Hello, today we will study extrema of functions of two variables. Firstly, I would like to remind you some ideas from calculus 1 with extrema of function of one variable. Okay, so let's consider the function y equal to f of x. We have two kinds of extremas, right? So we might have local extrema and we might have global extrema. Global extremas are, usually we find global extrema on some closed interval. That's what we did in calculus 1. Let's say on some closed interval. And local extrema is about, you might have maximum in here, you might have minimum in here, but that is just in a neighborhood of, of some point. It's just very locally. Makes sense? So that's why local extrema. But for both problem, we still need to deal with critical point. What are critical points? So critical points are points where the first derivative equal to 0 or the first derivative does not exist. When the first derivative is equal to 0, we are in this situation. But when the first derivative does not exist, we may be in the following situation. In this case, at this point, the left derivative and the right derivative are not equal. So that's why the derivative does not exist, right? But the function still attains local minimum at this point. All right, so how to do that for function of two variables? We use almost the same idea for function of two variables. Okay, so let me show you the picture. Okay, we have the following picture. So for function of two variables, we have a surface. For example, we have z equal to f of x. So we might have maximum. The maximum in this picture is, I would say, local maximum, right? But at the same time, that is global maximum if we just restrict the domain in the rectangular, right? So it's okay. But be aware about local maximum, right? That means the highest point in some neighborhood on the surface. That is not the highest point on the whole domain. So you can imagine like you climb to a mountain, right? So sometimes you get local minimum, but the highest part of the mountain would be global maximum. Sometimes I mess up. Like sometimes you can see the maximum of some neighborhood, right, of some piece of surface, but the global maximum of the surface would be the top of the mountain. Okay, let's look at this, right? So here's the definition. Here's the definition of relative extrema or global extrema. So if you have function f, right, and we say the function f has a relative minimum or global minimum at x0, y0. If you see the function value f x and y greater than or equal to f of x 0, y0, means the function value at x0, y0 is the minimum in some neighborhood, right? So you see in an open disk containing x0 and y0. So here's the picture. I just told you about the mountain, right? So in this picture, we would think that, yeah, the highest point is in the z-axis, right? But at the same time, if you just look around that, you still have some points like here, you see, and like this. You see, those are local or relative minimum. Similarly, we can define, a function has a relative maximum if the function value at that point is bigger than or equal to any function value at other points in an open disk containing x0 and y0. All right, so for a function of two variables, we also have critical points. Okay, so let's talk about critical points. Here's the definition of critical points. Function f is defined on some open region R containing x0, y0. The point x0, y0 is a critical point for x if one of the following is true. You see, the partial derivative with respect to the x equal to 0 and partial derivative with respect to the y equal to 0. That is for the first case of function of one variable, when the first derivative is equal to 0. So for function of two variables, they require two partial derivatives, f with respect to the x and f with respect to the y equal to 0. The second case of critical point is when one of partial derivatives does not exist. You see? So let's go back to the slide here, okay? So for this case, for function, let me summarize this. For function of two variables, z equal to f of x and y, critical points are points where fx equal to fy equal to 0, or fx or fy does not exist. So you see, this corresponding to two cases in here. The first one and the second one. And of course, you know, the function will attain extrema at those points, okay? For local extrema. For global extrema, the picture is a little bit different, so we'll talk about that later. But today we just talk about local or relative extrema. All right, let's consider the following example. Let's f of x and y is 2x squared plus y squared plus ax minus 6y plus 20. So you would recognize this is some kind of paraboloid, right? Paraboloid. They ask us to find the relative extrema. So the first step would be we need to find partial derivatives, right? Let's find fx, x and y. That is 4x plus 8. You just differentiate this function with respect to the x. And you find fy. xy is 2y minus 6. Since the partial derivatives, you know, f with respect to x and f with respect to the y exists, right? Exists everywhere. So we have only one case when f with respect to x and f with respect to y equal to 0. We don't have another case. Make sense? So in order to find all critical points, we just put this partial derivative equal to 0. The second step is solve fx equal to fy equal to 0. Alright? So from here, I get 4x plus 8 equal to 0 and 2y minus 6 equal to 0. From here, I solve for x, I get x equal to negative 2 and y equal to 3. That means the function has only one critical point. Function has only one critical point. Okay? So that means, you know, the function may attain maximum, local maximum or relative minimum at this point. But we still don't know yet about this point is local maximum or local minimum. Anyway, I can plug these points, you know, these values into the function to find the function value. Alright? So let's do that. Let's find f of negative 2 and 3, right? Let's find f of negative 2 and 3. That is 2 times negative 2 square plus 3 square plus 8 times negative 2 minus 6 times 3 and plus 20, and you simplify that, you get 3. All right, so now how to guess if this is local maximum or local minimum? It's very interesting, right? But you know, it's pretty easy. You know, sometimes it's pretty easy. So you might choose a very close point to this guy and plug that point into the function to see if the function value is bigger than 3 or smaller than 3. So let's say I want to pick, let's say, you know, the easiest point is 0, 0. 0, 0 is not very close to -2 and 3. But let's try this, right? Let's try 0, 0. And you plug into the function, you get f0, 0. It's just equal to 20, which is greater than 3. So this point is local minimum. All right. Now let's consider the second example where the partial derivative may not exist. All right. So example 2. Let fxy equal to 1 minus x squared plus y squared to 1/3. Let's find the relative extrema. Of this function, okay? So the first step is find f partial derivative f with respect to the x. We differentiate that, we use the chain rule. The derivative of 1 is 0. So if we use the chain rule, I have, this is the u. So basically I have u to 1/3, right? U to 1/3. Let me write here u to 1/3. Derivative is 1/3, u to -2/3, and then times u prime. Of course, in this case, you know, we differentiate with respect to the x. So according to this, I will have -1/3, the negative because we have negative in the function in here, okay? And then u, that is x squared plus y squared to -2/3 times derivative of u, which is x squared plus y squared with respect to the x. That gives us 2x. So basically I can write that is -2x over 3 x squared plus y squared and 2/3. Because, you know, we just flip this, right? We have negative in here, so we just flip it to the denominator. Similarly, we can find partial derivative of this function with respect to the y. Okay, so f of y, f with respect to the y, equal to 1/3. And again, I have x squared plus y squared, here -2/3, and then times 2y. So I have, that is -2y over 3 x squared plus y squared, and here I have 2/3. So this is our partial derivative, and it's obvious that, you know, partial derivatives do not exist at 0, 0. You see that? Because, you know, when x equal to y equal to 0, the denominator is 0. So f with respect to the x and f with respect to the y, they do not exist at 0, 0. That means 0, 0 is one critical point. Okay, so this is quite interesting, you know, in this situation. If you consider the first case when fx equal to fy, right, and equal to 0, you still get 2x equal to 0. and 2y equal to 0, and x equal to y equal to 0. So 0, 0 is a critical point for the first situation when but be careful with this, right? I just do that very naively, okay? Because we still need to consider denominator. In the second case, fx or fy does not exist. So you still see x equal to y equal to 0. Of course, if we say correctly, right? So that is not the solution of the first case, because in order to solve fx equal to fy, we have to exclude all point x, y, such that, you know, x squared plus y squared is not 0. So that is the case. So that is still not the solution of the first one. Still not a solution. So in this situation, we have only one case when x equal to y equal to 0. And in that situation, fx or fy does not exist. So 0, 0 is critical point. Sounds good. Now, we have only one critical point, so I can plug 0, 0 into the function. Our function is this, you see? Our function is good at 0, 0. The function is defined 0, 0. So I plug 0, 0. I get at 0, 0. The function at 0, 0 is equal to 1 minus 0, which is 1. So, is it minimum or maximum? Okay, so we still don't know about that. But again, we may guess from the definition of the function. From the definition of the function, so we have, you know, fxy equal to 1 minus cube root. I can write cube root of x squared plus y squared, right? Cube root. Since x squared plus y squared is always greater than or equal to 0, so this value, this function is always less than or equal to 1. It turns out that 1 is not only local maximum, it is also global maximum. Right? Global maximum, because, you know, the function value is always less than or equal to 1 for any point x, y. So that is global maximum. All right? So, you know, we have two cases. You know, when the first case, when the function is good, the partial derivative are good. The function has only one critical point, and we see that, you know, actually this point is local minimum. But again, right, this point is also global minimum. And, you know, in example 2, we have the case when partial derivative do not exist. Okay, so in that situation, you know, we solve almost in the same way. We just plug 5 critical points and then plug that critical point into the function to see. Then we might test, you know, the function value to see if this guy is maximum or minimum. So I hope that, you know, 2 examples are clear enough, and you can see actually this is some kind of similarity of calculus 1, right? First, 5 critical point, and then see, you know, the function value at those critical points. In calculus 1, in calculus 1, we have the first derivative test. Okay, we have the first derivative test. It says, so if you have function f of x, y f of x, and then you have, for example, 2 critical points, right? Let's say x1 and x2 are 2 critical points. So you may use the first derivative test to test the local maximum, local minimum. So you make the chart. That is x. This is x1. Suppose x1 less than x2, and here Suppose that the function is defined from negative infinity to positive infinity, but that's okay if the function is defined on some interval. Here is the first derivative, here is the function. So at x1, x2, the first derivative is 0. You just need to test. You just need to test the sign of the first derivative in here and the sign of the first derivative in each interval. So if the first derivative, for example, okay, it's just example. If this is negative and this is positive and this is negative, so if the derivative is negative, the function is decreasing. If the derivative is positive, the function is increasing, and so on. So that means in this case you will have minimum, and this is local minimum, right? And here is local maximum. So that's what we did in calculus 1. All right. Now we still have the second derivative test. Okay, this is the first derivative test. How about the second derivative test? So suppose x1 and x2 are critical points. You don't do with the first derivative. You go ahead to differentiate to find the second derivative, right? And you plug x1 and x2 into the second derivative. You get, if the second derivative x1 is less than 0, so that is your local maximum, right? And if the second derivative at x2 less than greater than 0, this is local minimum. The reason of this, because is that if the second derivative is less than 0, the function is concave. So if the function concave, the graph look like this. So that's why this guy should be maximum. You see this? If the second derivative is greater than 0, the function is convex. So I write concave in here. The function is convex. And then the function convex means the graph look like this. So that means that at x2, the function attains local minimum. Okay? So let's see. How does this work for function of two variables? Okay? All right. Now let's consider function of two variables. We have y equal to, no, not y, z equal to f of x and y. Okay, so we learn how to find partial derivative of the second order. Is that correct? So let me list all of them. So first I have fx, and then I have fy, and from fx I might have fxx. From here I have xy, and here I have fx yy, and here I have fyx. We mentioned several times about the second derivative. The mixed derivative fxy and fyx are not always equal. But for good functions they are equal. All right. But basically, in this course we will see all examples where the mixed derivatives will be equal. So that is not a big deal. If you do complex analysis, so you would see many examples where the mixed derivatives are not equal. Okay, now let's talk about the second derivative test. Okay, for function of two variables. So we have a function f, x and y, and suppose that this function has continuous second partial derivatives, right? we say fxy, fyx are continuous on an open region. We don't have interval in this case because function of two variables containing point A, B. And partial derivative at AB equal to 0. Okay, so both partial derivative with respect to the x and with respect to the y equal to 0. So, you know, this condition just say, yeah, A and B is critical point, right? It's critical point. That means we don't have another case where when the first partial derivative does not exist, okay? So we have only one case, partial derivatives at this point is equal to 0. All right, now we will calculate the following value. D equal to f xx ab f xy, no, f xyy at ab minus fxy ab square. So you may guess, yeah, why we don't have fyx in this case? Because in this case they are equal already. So we have three cases. The first case, I write like this: if d greater than 0 and fxxab greater than 0, so this is local minimum. Okay, if d greater than 0 and f of xx ab less than 0, then this is local maximum. Okay, so when d is less than 0, this point is called saddle point. I would write like this: saddle point. And when d is 0, so no information. Okay, so we didn't say anything about saddle point, but you know, you might take this as a definition of saddle point. I will show you a picture of saddle point later, but you can imagine about the saddle, right? The saddle, like the saddle of the horse or something like that. But before we move to an example, I would like to mention one thing: the value of d, the definition of d. You see, look at this, the definition of d. That is fx, fyy, and minus fxy squared. So, you know, if we look at this from the point of determinant, right? This is just the determinant of the following matrix. That is determinant of fxx, and here fyy. In here you have fxy, and here you have fyx. So if you calculate determinant of this matrix at AB, you will get the value D, right? So say if the determinant of this matrix is greater than 0, and the value, you know, the value f second partial derivative fx at AB is bigger than 0, that is local minimum. And you know, d greater than 0 and this guy is less than 0, so that is maximum. And if this is less than 0, so that is saddle point. That means the function does not have local extrema at this point. And when this is equal to 0, no information. So the same situation, for function of one variable, if the second derivative equal to 0, so that is just a inflection point. All right, so let's consider the following example. Apply the second partial derivative to determine local maximum and local minimum. Example. Let's consider the following function. F x and y equal to negative x cubed plus 4xy minus 2y squared plus 1. Right? So we need to determine local extrema. All right, now let's find derivatives, right? The first and second derivative. I need to find f with respect to the x, that is negative 3x squared plus 4y, and f with respect to the y is 4x minus 4y. Okay, and now we need to find the second derivatives, right? I would write in this form. So from here I get f(xx) is equal to negative 6x, right? And then f(xy) is equal to 4, right? For the second one, I get fyy is equal to negative 4, and fyx is equal to 4. So I can go ahead to set up the determinant, the determinant of D. Makes sense? But but maybe we need to find critical points first, because in any cases we need critical points. So I find critical points. I will set fx equal to 0 and fy equal to 0. From here I get negative 3x squared plus 4y equal to 0, and 4x minus 4y equal to 0. From the second equation, we see x equal to y, right? And we plug this into the first equation. We get negative 3x squared plus 4x equal to 0. We factor this out. We get x negative 3x plus 4 equal to 0. And we have two zeros. X equal to 0 or negative 3x plus 4 equal to 0. So for this equation, it's easy to see that x equal to 4 over 3. That means this function has two critical points. The first one is 0, 0. The second one is 4 thus and 4 thus. Because x and y are equal. Don't forget this. Alright, so we have two critical points. Now let's go ahead to test, right? Let's go ahead to test. So we have to look back the second derivatives in here. I have to copy this. I don't know if I can do this like just make a copy or not, but anyway, I can just copy, right? So I write here the d, let's say the small d equal to negative 6x and here I have 4, here I have 4, and here I have negative 4. Okay, so that is 24x minus 16. That is the D. And of course, you know, D depends on X and Y. In this situation, we don't have Y, but you know, D generally depends on X and Y. All right, we already have D. We already have 2 points in here, 0, 0, 4 thus, 4 thus. Now we just plug each point into D, and then see, you know, how D looks like. All right, so let's say at 0, 0. The D at 0, 0 is negative 16, which is less than 0. So this is saddle point. We don't have any, you know, extrema at this point. At 4 thus, I plug 4 thus into D. I get 24 times 4 thus. I don't have Y, but that's okay. Minus 16. So that is 16, right? 16 is bigger than 0. That means we might have, you know, critical points in here. But in order to determine this guy is local maximum or local minimum, we still need to check the value of partial derivative f xx. So that is negative 6x, right? At negative 6x, you know, when x equal to 4 thirds, that is negative 8. So you just plug 4 thirds into this, you get negative 6, 4 thirds, you get negative 8, which is less than 0. Now we compile 2 conditioning here. The first one, D greater than 0. The second one, second partial derivative with respect to x is less than 0. So by the second derivative test, this is local maximum. Okay, this local maximum. So I think, you know, it's pretty easy to use the second derivative. We just follow ideas from calculus 1. 5 critical points, 5 second derivative. But the only difference in this situation is D. Okay, it's just D. So you have to find mixed derivatives, and then, you know, plug everything into this formula. You know, I prefer to write in the form of determinant, because sometimes you don't remember this. But it's easier for me to remember the determinant. Make sense? So depends on you. Yeah, you do whatever you want. All right. So I think it's very good enough for today. So I will make another video on absolute extrema, and we might consider examples where the second derivative test fails. Okay. Anyway, we see you in the next video. Thank you.